Hi guys, welcome to lesson 4 of our virtual learning experience. I wanted to start off this class by just telling you how proud I am of you guys. I know this is a huge adjustment. I am here to support you. Just a few things I wanted to start with just in case there are some people having some difficulties. Number 1, at the beginning of each class, make sure you read the full announcement. I try to put a lot of detail in there in case you guys have any questions. Always check the announcement and always check the classwork page. The classwork page is where you're going to be turning in your assignments. A lot of you have just been doing the Edpuzzle without pressing the turn in button, which has been fine, but please go ahead and at the end of every Edpuzzle press turn in. It just makes everything a little bit easier for everybody. In addition to that, I just wanted to let you know that today, halfway into the class period, I will be available on Google Meet. So if anyone wanted to join that and just ask some questions virtually instead of having to send me an email, you can always do that. I am always available on email, so you can always do that as well. Yeah, so that's pretty much the idea. We'll get started with today's lesson now. So today we're going to continue working on right triangles, specifically some special right triangles today. And their properties. We're going to continue with the Pythagorean theorem, and we're going to go with that. So if you have any questions, like I said, you can always pause, send me an email, jump on Google Hangouts. But overall, we're just going to get started with the lesson for today. All right, so the first type of special right triangle we're going to talk about is an isosceles right triangle. Now, an isosceles right triangle has a nickname, which is called a 45, 45, 90 triangle. Why do you think its nickname is the 45, 45, 90 triangle? So hopefully the 90 came pretty easy to you. The 90 comes from the fact that it's a 90-degree angle here. And then how many degrees are in every triangle? Every triangle has 3 angles that add up to how many degrees? Good, they always add up to 180. So if it's 180 minus 90, that means we have 90 degrees left over. And since this is an isosceles right triangle, we know that the base angles need to be congruent. So that remaining 90 degrees has to get divided up evenly, which makes each of them worth 45 degrees. So that's why it's called a 45, 45, 90 triangle. It represents all of the degrees in the triangle. So moving ahead, we're going to talk about this 45, 45, 90 triangle, specifically about its side lengths. So we're going to focus on, if I know the size of one of the legs, can I find the length of its hypotenuse? So if I know that just one leg, let's say the leg that's line segment TR is 5, can I find the other 2 sides? Because normally when it's a regular right triangle, I need to know 2 in order to find the third. But when it's a 45, 45, 90 triangle, I actually only need to know 1. So if I know 1 is 5, then I know line segment RI is what? Line segment RI is also 5. And now that I know that, I can go ahead and find line segment TI. Is TI a leg or a hypotenuse? It's a hypotenuse, meaning it's going to be represented by C when we use the Pythagorean theorem. So we're going to now solve for C. And we're going to do 5 squared plus 5 squared equals C squared. This becomes 25 plus 25 equals C squared, which becomes 50 equals C squared. And then what do we have to do to both sides to get C on its own? Totally isolate C. We need to take the square root. So that now becomes the square root of 50 equals C. Is this done though? No, because we need to simplify. Okay, so if we have the square root of 50, I can break that down in a couple different ways, 5, 10, 2, 25, and I like 2 and 25 because 25 is what type of number? 25 is a perfect square, which means 25 gets broken down into a pair right away. Now, could you have picked 5 and 10? Totally. You still would have gotten 2, 5, and 5. But by breaking it down into perfect squares, you can actually sometimes alleviate some work for yourself. And you'll see that in subsequent problems that we work on. So now we break it down into 2 times 5 times 5. The pair of 5's leave the radical as 1, and all that's left is 5 radical 2. So our answer for what the value of C is 5 radical 2 is the value of C. 5 radical 2 is the value of C. So I'm going to keep track of that on this little table I have in the bottom left-hand corner. When the legs were 5 in this isosceles right triangle, the hypotenuse was 5 radical 2. And we're now going to do this a couple times. We're going to solve and simplify, solve and simplify, solve and simplify, and see if we can notice any patterns going on here. All right, so now instead of 5, I'm now going to work with the number 7. So if I know Ri is 7, I know Tr is 7, and then I'm just going to look for value C. So when I'm using 7 as my leg, what are the values of the hypotenuse? 7 squared plus 7 squared equals C squared. 49 plus 49 is 98. Then we take the square root of both sides, and we then need to get square root of 98 equals C. Then we need to simplify. What do you get when you simplify the square root of 98? So if I simplify the square root of 98, I get 2 and 49. You could have broken it down a couple other ways, but 2 and 49 are the way that come to mind because 49 is what type of number? A perfect square gets broken down into 7 and 7. So we have the square root of 2 times 7 times 7. The pair of 7's leave, and we're left with the square root 7 times the square root of 2. So that's our value of C, 7 square root 2. 7 square root 2, and we'll add it to our table so we can see if we start recognize any patterns. All right, that's interesting. Maybe you already see a pattern, but there's something that 7 and 5 share in common. 7 and 5 are both prime numbers, and they're both odd numbers. So let's see when I use an even number that is not prime and see if that pattern that maybe you already are starting to see still works. So now I'm going to make TR 4. 4 is not prime. It is not even. So let's try to see what happens there. Both of those are going to be 4. 4 squared plus 4 squared equals C squared. 16 plus 16 equals C squared. 32 equals C squared. Then I take the square root of both sides. I get the square root of 32 equals C, and then I need to simplify. Square root of 32. Now, you totally could break this down into 8 and 4, and that's probably what your brain immediately jumps to because those are the numbers that come to your head pretty quickly. But what I want you to start to think to yourself is there any perfect squares that I can divide out? And there are in this case. Now, while 4 is a perfect square, let's try to think even bigger. 32 can get broken down into 2, and what other number? 16, and 16 is a perfect square. 16 square root is what? Good, 16 square root is 4. 4 and 4. So, while 4 is not prime, and I could totally break it down further, I don't need to because they're already paired. That's our goal, is to find pairs. So yes, it's always good to go all the way down to prime factors if you're stuck, but if you see pairs or you see a perfect square just to be taken out right away, you can stop right there. And you'd get the square root of 4 times 2. The pair of 4's would leave. 2 would be left, making the answer 4 square root of 2. 4 square root of 2. So when our leg was 4, our hypotenuse was 4 square root of 2. Now maybe you started to see a pattern, and I know I'm starting to see a pattern. So I'm going to give you this question. What if you know that the leg is 6? What is the hypotenuse going to be based on the pattern you're starting to see? So you've made your guess. Let's see if your guess is right. So 6 squared plus 6 squared equals C squared. 36 plus 36 equals c squared. 72 equals c squared. Take the square root of both sides. Square root of 72 equals c. We have to simplify square root of 72. I'm going to think to myself, well, I could easily use 8 and 9, right? Think to myself, is there a perfect square hidden there? And there is, right? So I can take out 2 and 36. 2 is prime, that stops there. 36 gets broken down into 6 and 6. Since they're already paired, we don't need to break them down further. 2 times 6 times 6. The pair of 6's leave. 2 is left. 6 radical 2 equals c. 6 radical 2 equals c. When the leg is 6, our hypotenuse is 6 radical 2. Now let's see if we can try to come up with a formula to represent what's going on. So I'm going to erase what we have here. We don't need that anymore. In a 45, 45, 90 triangle, if the legs are, let's represent them with x, the hypotenuse is what? Whatever the value of x is, times radical 2. So the next type of problem we're going to look at is an equilateral triangle. Now this is a little bit of a step away from what we have been working on, right? Because we've been working on specifically what type of triangle for the past week and a half. We've been working on right triangles. And what do we know about equilateral triangles? What are some properties you know about an equilateral triangle? So some properties we know about an equilateral triangle. We know all of the sides are congruent. And we know all of the angles are congruent. All of the angles are specifically how many degrees? Good. All of the angles are going to be 60 degrees. And then this whole piece right here, right there, is going to be 60 degrees. But there is a perpendicular bisector in this equilateral triangle. And the perpendicular bisector is both cutting angle A into two congruent parts, cutting line segment BC into two congruent parts, and is doing so at a right angle. So if we focus just on triangle DAC, just that triangle, what type of triangle is that? Don't mind the train. Good, that's also a right triangle if we focus on just that half of the equilateral triangle. And how many degrees are right here at angle DAC? So if you did this correctly, you would figure out that the angle there is 30 degrees. Oh, I'll use my gray color. It's 30 degrees. So we just talked about a 45, 45, 90 triangle. Now we're going to lead into a 30, 60, 90 triangle. And we're going to largely ignore the other half of this triangle, but it is helpful for some parts of what we're going to learn here. So what I'm going to have here that we're going to start with is, if I know how long line segment AC is, let's say AC is 6, the length of it is 6. How long is line segment DC? The length of line segment DC, since this AD is a perpendicular bisector, we know DC is going to be 3. And what we don't know is going to be the length of line segment AD. That's what we want to find out. So in this 30, 60, 90 triangle, we have 6, 3, and something unknown. Now, is the unknown piece, is that a leg of the triangle, or is that a hypotenuse of the triangle? Good. B is a leg of the triangle. So our two legs are being represented by 3 question mark, and our hypotenuse is being represented by 6. Now, if we go back to some of our triangle inequality theorems that we learned back in our triangle chapter, we know that the side opposite the smallest angle is always the smallest side. The side opposite the largest angle is always the largest, and the side opposite the middle angle is always the medium length side. So we know our question mark is going to be somewhere in between 3 and 6, but our question really is, just how big is it going to be? And we can use, since we have 2 sides of a right triangle, we can use what to find it? That third side can be found using the Pythagorean theorem. A squared plus b squared equals c squared. So I just chose to put them in value of increasing amount. So a is the smallest side, so I made A the smallest, B the medium, C the largest, and go in order that way. So we know A is going to be represented by 3 for this first problem, plus B squared equals 6 squared. 3 squared is 9, plus B squared equals 6 squared is 36. We subtract 9 on both sides, and we get B squared equals 27. We have to square root both sides to get b equals the square root of 27. And now we need to simplify. What is the square root of 27 simplified? So if I go here to use 27, I want to ask myself, like I was in the past, are there any perfect squares stuck in 27? And there are. 3 can also, when you divide 27 by 3, you get what perfect square? You get 9 as the perfect square, which breaks down into 3 and 3, making it 3 times 3 times 3, and the pair leaves the radical as 3 radical 3. B equals 3 radical 3. That's our value here, 3 radical 3, and that's what I'm going to put down here in my table. If A was 3, B is 3 radical 3, and C is 6. All right, so now let's try that with some other numbers, with some other side length. Because it's an equilateral triangle with that perpendicular bisector, I can, instead of starting with the side, I can start with the hypotenuse. I can start with the smallest leg of A, and let's make that 5. If DC is 5, how long is AC? Good, it's going to be double that, it's going to be 10. So I'm going to say A is 5, C is 10, B we don't know. So let's plug that into our formula. 5 squared plus B squared equals 10 squared. 5 squared is 25 plus B squared equals 100. Subtract 25 from both sides. You get B squared equals 75. Then we're going to take the square root of both sides. We get B equals the square root of 75, and we need to simplify. What perfect square can you divide out of 75? Good, 25 is a perfect square you can divide out, and you'll be left with 3. So 3 is a prime. 25 gets broken down into 5 and 5. 5 times 3, the pair of 5's leave. You get 5 radical 3. B equals 5 radical 3. 5 radical 3, and that's what we're going to put in our table, 5 radical 3. So once again, when I did these examples like I did last time, we use the same type of number here, prime odd numbers. So let's use non-prime or composite even numbers and see if we get any different thing, because we can't really look at the pattern before we kind of look at the whole big picture. So I'm going to make AC is going to be 8. If AC is 8, how long is DC? Okay, it's going to be 4. And now we want to find B. So A squared, so 4 squared plus B squared equals 8 squared. 4 squared is 16 plus B squared equals 64. We're going to subtract 16 from 64. When you do 64 minus 16, what do you get? We get 48. Take the square root of both sides. B equals the square root of 48. Then we're gonna simplify. What do you get when you simplify the square root of 48? So we're gonna simplify it. Now, you can try to simplify it however you like. You can totally break up into 4 and 12, but I'm going to always be trying now to find and see if there's a perfect square that divides out. And I know that 3 and 16 also go into 48, and 16 is a perfect square of 4 and 4. And since there's a pair already, we don't need to continue the tree because they're already going to get taken out together. So we can say 3 times 4 times 4, the pair of 4's leaving us with a 3 inside. You totally could do it the long way. You can totally do it another way. As long as you're getting 4 radical 3 at the end, we're doing it correctly. So we knew that A was 4, and we see that B, that other side, is going to be 4 radical 3. All right, maybe now you can start recognizing a pattern developing. So what if I tell you for this next one that my value for C, my line segment for AC here, is going to be 6. Oh, we just did that one. Never mind. Let's say my value for AC is going to be 20. What is the value of A going to be based on the pattern so far? Good, the pattern is going to tell us that A is going to be 10. And what is the value of B going to be? Let's do the math quick and see if we're right. 10 squared plus B squared equals 20 squared. 10 squared is 100 plus B squared equals, what's 20 squared? 400. We're going to subtract 100 from both sides. We get B squared equals 300. We take the square root of both sides. And then we're going to simplify the square root of 300. 300 breaks down into 3 and 100. 3 is prime. 100 is a perfect square. What is the square root of 100? Good, it's 10 and 10. And then we can break that down. 10 times 10 times 3. The pair of 10s leave. And we're left with the square root of 3. B equals 10 square root of 3. 10 square root of 3. Are you starting to develop a pattern here? Are we seeing something that maybe we didn't see before? So, in these 30, 60, 90 triangles, the value of A, whatever that is, let's say we're given a value of A that is X. What is the value of B going to be? Good, it's going to be X square root of 3. And what is the value of C going to be? It's going to be 2x. Now, this is the next trickier one. What if I give you the value of C is, let's say I'll use a different variable here. Let's say the value of C is going to be, oh, that was weird, is y. What is the value of A, that smallest side? You're going to take y and you're going to divide it by 2. And then what is the value of B? It's going to be y divided by 2 times the square root of 3. All right, now let's just wrap that up really quick. We have a 30, 60, 90 triangle. We're always going to name the smallest side for these is going to be opposite the smallest angle, so this is going to be A. The medium size is going to be opposite the medium angle, so this is going to be B. Biggest side is going to be opposite the biggest angle, so this is going to be C. And a 30, 60, 90 triangle, if the smallest side has a given value of x, the biggest side is going to be double that value, and the medium side is going to be the value of the smallest side times radical 3. Alright guys, so you might have noticed the patterns that we just developed have a lot of square roots in them. So what I'm going to talk to you about at the very end is just talking about something called Pythagorean triples. So going back to like the first few videos I showed you a lot of times showing that a right triangle could have a side length 3, 4, and 5. Now this is different from a lot of the answers that you've been getting for the missing sides of a right triangle because all 3 of these numbers are whole numbers. A lot of times you're getting these crazy radicals or these really long decimals. But there are a few sets of Pythagorean triples is what they call, which is 3, 4, 5 is one of them. And those automatically will create a right triangle. If we test them with the Pythagorean theorem, they will work. And they're just good to kind of know a few of them in your back pocket. I do not recommend memorizing the whole list of them. There's infinite amounts of them. 3, 4, 5 is one that I'm going to show you. It happens a lot though. And the interesting thing is you can scale them up. So if 3, 4, 5 is a right triangle, so is 6, 8, 10. So is 9, 12, and 15. Can you list one more for me you think you can get there? Yeah, there's a whole bunch you can do, and all it is you would take each of the numbers in the triple of 3, 4, 5 and multiply them by the same scale factor. You can multiply them all by 10 if you wanted to and make it 30, 40, 50. And that's also going to be a Pythagorean triple, all just based on the 1, 3, 4, 5. There's a few other I'll show you. You don't need to memorize them, but like I said, it's just sometimes good to know. I'm going to just share with you 3 more other than 3, 4, 5, and just know that they can be scaled up or down. Even 0.3, 0.4, and 0.5 would also be a right triangle. So 3, 4, 5 is a Pythagorean triple. Some other Pythagorean triples are 5, 12, 13. 7, 24, 25. And the last one I'll share with you is 8, 15, 17. Like I said, you don't need to memorize them. I often get these ones confused. Sometimes I think it's an 8, 24, 25 because just the numbers are hard to memorize. The only one I definitely think is worth memorizing is 3, 4, 5 always being a right triangle. All right, that about wraps up what I wanted to share with you guys today. There is practice problems that I want you to do now to go onto Classroom. You don't need to hand them in, but I do want you to practice them and check your answers. The answers to those practice problems will be posted to Classroom next class. And if it's not too late, I will be on Google Meet for the last half hour of class. And if you missed it, I'm also going to be available during some other classes today. So if you wanted to see if you could catch me another time, just send me an email and I can send you a link, or we can set up a separate time to talk. All right, guys, have